We're going to start with parallel RLC circuits. Then, when we come back from the break, we're going to talk about series RLC circuits. And then I believe I have a day dedicated to just working some problems and all that kind of good stuff. And then I have 2 days dedicated to the analysis of what I call general second order circuits. And the reason I do that is because the textbook that we use for this class has a very, in my opinion, a very good and detailed description of how to analyze parallel RLC circuits. It has a good and detailed description of how to analyze series RLC circuits. And then it stops there. And the overwhelming majority of RLC circuits that we are going to be tasked with, excuse me, analyzing, designing, and all that kind of good stuff, don't necessarily easily fall into one of those two categories. So we spend some time developing the rules and relationships for analyzing any second order circuit. So anything that contains two energy storage elements which are not coupled together. Okay. So for a parallel RLC circuit, let's consider something simple to begin with, where we have, let's say, a current source, IS, connected to some resistor RS, and let's see, how am I going to draw this guy? Here I will have some resistor R, some inductance L, and some capacitance C. And let's define our capacitor voltage, VC of T, like so. So that the capacitor voltage VC of T is also the voltage drop over our inductor L, as well as the voltage drop over our resistor R, because all of those elements are connected in parallel. And I'm going to call this current through my capacitor IC of T. I'm going to call the current through my inductor IL of T, and the current flowing through my resistor IR of T, like so. All right, so at T is less than 0, what should we observe in this system? All right. So for T is less than 0, assuming that our circuit has been on for a very long time, we should see that the inductor and the capacitor are represented by their DC steady state equivalents, which in this case means that our inductor will behave like a short circuit and our capacitor will behave like an open circuit. So treating our inductor as a short circuit and our capacitor as an open circuit, it should be fairly easy to see that our inductor will have a current of IS divided by, just a current of IS flowing through it. And our capacitor will have a voltage drop of 0 across it, which means that our inductor has some amount of stored energy. Our capacitor does not, and our resistor R is really doing a whole lot of nothing for right now. Okay. When that switch opens up, that effectively disconnects the RLC circuit from the current source side, and we should see that our inductor starts transferring some of its energy to the capacitor and to the resistor. So it's very similar to what we saw in our transient analysis of first order circuits, so RL and RC circuits, but now we have an extra energy storage element where energy can just be passed back and forth before everything gets converted to heat by the resistor. So during the transient condition, we can develop a differential equation. So for t greater than or equal to 0 plus, we can say that IR of t plus IL of t plus IC of t is equal to 0. Right? Kirchhoff's current law has to hold. And we can express all three of these currents in terms of that common voltage VC of t, right? So IR, will be VC over R. So we'll have VC of t divided by R. For our inductor, that's going to look like 1 over L times the integral from T naught, which is some point in time where we know what the inductor current is, to T of VC of X dx plus IL at T naught. And our capacitor current is C times the derivative of our capacitor voltage with respect to time. So this is what's known as an integro differential equation because it has both an integral and derivatives in it. So what I'm about to do next is greatly simplify this equation in one simple step. So I'm going to turn this integro differential equation, which can be a bit of a pain in the butt to look at, into a second order differential equation simply by taking the derivative of both sides, right? So I'm going to take the derivative of both sides and I'm going to rearrange things slightly, okay? So if I take the derivative of the capacitor contribution, I'm going to have C times the second derivative of my capacitor voltage. Then I take the derivative of the resistor contribution, and I'm going to have 1 over R multiplied by the first derivative of my capacitor voltage. And then when I take the derivative of the integral, I'm just left with 1 over L times my capacitor voltage. And when I take the derivative of IL at T naught, that's just a constant. So I take the derivative of a constant, I get 0. And so I have a homogeneous, because it equals 0, second order differential equation. I'm going to make one small change here. I'm going to divide both sides by C so that the coefficient on my second derivative term is 1. Not really going to have any purpose for doing that just yet, but it'll be very important when we get to our general second order circuit analysis. So I can take that C and I can put it down here and down here. And I have, again, a homogeneous second order differential equation. So because not all of you have had Math 245, we are going to make an educated guess as to what our capacitor voltage waveform VC of T should be. And we're going to use the exact same educated guess that we used in Engineering 221. So I say that in my previous experience, it seemed like it was an exponential response. So that seems like a pretty good place to start from for here. So if we guess that VC of T is of the form A E to the ST, and we plug that guess into our differential equation, what's going to happen? What's the second derivative of AE to the ST? Wouldn't it be A times S squared? Because we're taking the derivative, right? Not the integral? Yeah. So this first bit is going to look like S squared A E to the ST. Then we're going to have S divided by RC A E to the ST plus 1 over LC A E to the ST is equal to 0. And then I am going to group terms so that I will have A multiplied by S squared plus 1 over RC times S plus 1 over LC, all multiplied by E to the ST is equal to 0. And this guy here in the middle is my characteristic equation. Okay. So it's my characteristic equation because if A is 0, this is a trivial solution, everything is 0, right? So that's effectively what we would have if our inductor current was 0 and we never had any stored energy at all. E to the ST will approach 0 if S happens to be negative and we allow enough time to occur. But we can find that there are going to be specific values of R, L, and C that will force this characteristic equation to be 0. And we're simply solving for the S's, which are the natural frequencies of the system, that make that happen. Now, this is slightly more difficult than what we did in Engineering 221 because we have a second order system as opposed to a first order system. But our characteristic equation here is a second order polynomial or quadratic, which means we can use good old 8th grade math to figure out what values of S make the system go to 0, right? Pardon?
Solve the differential equation. Instead of just making the guess, if you already knew the answer.
I don't know. It's been a really long time since I took Math 245. I'm saying this is a guess, but this is literally what I would choose regardless of if I had circuits 1 to begin with. The reason why I say that is because I need some sort of mathematical function to where the second derivative and the first derivative and the function itself combine together to be 0, which means they all need to have the same form. And the only thing that satisfies that is an exponential function. So that's, I can't remember how to do the actual mathematical description of how you would choose that, but that's the reason why it's going to work. Caleb.
The 1 over RC.
Yeah, I'm multiplying it by S. Yeah, so that I can see that I have a coefficient of 1 times S squared, a coefficient of 1 over RC times S, and a constant term of 1 over LC, because I'm about to use the quadratic equation. All right. So my natural frequencies or eigenvalues or whatever kind of hippie thing you want to call it, depending on what math you've been in and all that stuff, for this system is going to be given by negative 1 over RC, right? So negative B plus or minus the square root of B squared minus 4 times A, which is 1, times C, which is 1 over LC, all divided by 2A. And so what I'm about to do now is I'm just going to move this pesky 2 down here from my denominator up into my numerator. And so what that's going to give me is negative 1 over twice RC plus or minus the square root of 1 over twice RC quantity squared minus the square root of 1 over LC quantity squared. In electrical engineering, this factor of 1 over 2 RC has a special name, and this factor of square root of 1 over LC also has a special name, okay? So we're going to define alpha to be 1 over twice RC for our parallel RLC circuits, okay? Alpha is what's called the Neper frequency. So it has units of Nepers, which are a dimensionless quantity per second, and it represents the attenuation of our signal over time. So it is not the same thing as a time constant, but conceptually it is very similar. So it represents the decay of our signals in time. We can also define a term omega naught, which will be the square root of 1 over LC and this will be the resonant frequency of our system measured in radians per second, where radians is again a dimensionless quantity. The resonant frequency, it has lots of different measures of importance in circuits and systems as a whole, okay? So if we had a steady state sinusoidal system, the resonant frequency would be the frequency at which the impedance of our network is purely real. So all of the capacitive reactance would be exactly canceled out by the inductive reactance. And if we were looking at this circuit, we'd find that that is exactly what would happen, okay? The resonant frequency is the frequency at which effectively, I'm trying to think of the best way to put it. How many of you guys have heard of the Tacoma Narrows Bridge? So the Tacoma Narrows Bridge was a bridge designed in the late 50s, I think. And it had a particular resonant frequency which was able to be matched by the speed at which the wind was blowing it, okay? So effectively, this bridge had a small amount of vibration And then the wind kept hitting it at that exact same frequency, and it caused the amplitude of those vibrations to keep increasing and increasing and increasing until the bridge finally tore itself apart. This was a huge, huge infrastructure project that I think lasted less than a year before it ripped itself apart. There's a really good explanation of resonant frequency. If you guys have Discovery Plus, watch some season 1 Mythbusters, and they built a trying to do a recreation of the Tacoma Narrows Bridge using pneumatic actuators to try to force a bridge to rip itself apart. But effectively, it's the frequency to where if you put any extra energy in at that frequency, it gets compounded and compounded and compounded over and over again. You could think of it as kind of the frequency at which naturally occurring positive feedback would occur. So it's going to build and build and build until it tears itself apart. That's actually a pretty reasonable interpretation of what's going on. All right, so in terms of our Neper frequency and our resonant frequency, we now have S1 is negative alpha plus the square root of alpha squared minus omega naught squared, and S2 as negative alpha minus the square root of alpha squared minus omega naught squared. Okay. So this is our general solution to this characteristic equation, but we actually have 3 different instances that can occur here. Okay. So sorry, that shouldn't be I. Let's close. If S1 does not equal to S2. Okay. So if F1 does not equal to S2, if we put our frequencies back into our original guess here, right? So we have A e to the ST. We would have A1 e S1 to the T plus A2 e S2 to the T. So effectively, superposition tells us that if we can add the 2 results together, and the total result also has to be a solution. Okay, so simply substituting S's back into our initial guess value, we get, our response VC of T will be of the form A1 e to the S1T plus A2 e to the S2T. In both cases, S1 and S2 will be real and negative. So they're both going to cause our capacitor voltage to approach 0 as time increases. All right. This system is what is called an overdamped system. So in an overdamped system, we will see that our energy storage elements lose their energy very slowly. Effectively, it takes a long time for our capacitor voltage to settle to its final value of 0 in this case, after it had some energy stored, because it's going to transfer it back and forth with the inductor while gradually losing some to the heat, to be converted to heat by the resistor. Okay. So it's just going to be a pretty smooth curve. It just takes a long time to settle. And I'm going to draw a curve of what it looks like short for a simple system. Okay. Our second condition is going to occur when S1 is equal to S2, okay? So if S1 and S2 are equal,
We say S is what represent.
S is the natural frequency of the system. So it describes how it settles to its final value. So what are the constraints that would make S1 and S2 equal to each other?
If your root becomes 0.
Right, so if alpha and omega naught are equal, the square root is 0, square root bit here is 0, and so we have S1 is negative alpha and S2 is also negative alpha, right? So for S1 is equal to S2, that means that alpha has to be exactly equal to omega naught. Actually, let me go back to do something here because I forgot to do it, and this might be a good way to explain things as well. For S1 to not equal to S2, we want alpha to be greater than omega naught as another way to classify what's happening there. My apologies for doing it oddly, okay? So we have alpha is equal to omega naught, then we know that S1 is equal to S2. And so if we tried to plug S1 and S2 back into our original equation, our original guess, we'd run into a little bit of an issue, because since our characteristic equation is quadratic, we know that we need to have two solutions, but we would effectively only be able to handle a single initial condition on our system. So in Math 245, and then again in your electrical engineering systems and signal class, so ELEN 321, you are going to learn that when you have repeated roots, there is a particular response equation for that. And that response equation is going to be of this form. VC of t is equal to A1 t e to the negative alpha t plus A2 e to the negative alpha t, okay? So the inclusion of this time term here in our first part of our response is how we're going to get to accommodate the initial condition on effectively our inductor, okay? So we need two coefficients out front because we have two energy storage elements, all right? This is what's known as a critically damped system. And the response curve for a critically damped system is going to look very similar to the response curve for an overdamped system, except that it settles to its final value quickly, okay? So for a critically damped system, that's really a best case scenario, all right? It's going to settle to its final value in the shortest amount of time without having any overshoot or ringing, okay? And then our third condition is if S1 and S2 are complex conjugates. Okay. So this happens when alpha is less than omega naught. And using Euler's identity, we'll find that our capacitor voltage will be of the form B1 cosine omega dt plus B2 sine omega dt. All of this multiplied by a factor of e to the negative alpha t, where omega d is simply the square root of omega naught squared minus alpha squared. So we call this kind of system an underdamped system. So in an underdamped system, we'll hit our final value very, very quickly, but we're going to wind up overshooting it and then correcting, and we'll see that we're going to have ringing occurring. So if I graph these guys, here's VC of T, here's T. Let's do critical damping in blue. So we should just see simple exponential decay. For overdamping, we'll do that in orange. Same generic shape, but takes a really long time to settle. And then finally, we'll do underdamping in green, where omega naught is greater than alpha. And we'll see that it gets to its final value really quickly, but then rings, and it has an envelope that looks very similar to an overdamped response.
Eight to the underdamping graph correspond to points on the overdamping graph.
It depends. So if our circuit is as much underdamped as it is overdamped, meaning that we were as far away from critical damping as we were on both sides, then yes, like this exponential decay forms the envelope of this sinusoidally occurring exponential decay as well, right? And it should make sense here. The reason why I say that, if we look at this guy, it's the sum of two sinusoidal signals, and then it's being multiplied by an exponential decay. So if this bit were 1, this would just look like a sine wave, right? But the envelope is what's given at here. So if the alpha value for our underdamped system was the same as the alpha value for an overdamped system, then those would exactly match. It would just be points on that curve. All right. Okay, so all of these relationships that we've developed are summarized in the table that I provided you guys. It'll be uploaded on Moodle. It will be given to you for your exam. But there is one small difference on what is on here than what we've talked about, okay? The only difference is the inclusion of a y at infinity term, right? That y at infinity term is just what happens when our switch goes in the opposite direction, just like what we saw in the engineering 221 class, right? So when we have a system where a source is being added in, it will settle, the system will settle to some finite value, and that's taken care of in that y at infinity term, all right? Now, another thing that I have included on here is the derivative of our response as a function of time. And the reason why I have included that will be pretty obvious when we do some circuit analysis here. But there are derivative-based relationships for current and voltage in capacitors, and derivative-based relationships for current and voltage in inductors. And we're going to need those derivative-based relationships in order to successfully predict how these circuits are going to behave. So what I would like us to spend the remainder of the class doing is working out a simple problem. So let's say that we have the following circuit. Let's say that we have a 5-volt source. Let's call this, actually, you got to tell me what size of resistor we want here. We're going to have 2 resistors. Just make them on the same scale. 1K and what else? 1K and 10K, okay? So let's say we have a 1 kilo ohm resistor here. $10 kilo ohm resistor here. All right. What size should my inductor be? Pardon? 4 Henrys. All righty. And what size should my capacitor be? All right, and now a critical question. Does our switch open at t is equal to 0 or close at t is equal to 0? Open? All right. Okay. So we are going to analyze this circuit and we're going to walk through the steps. These are the exact same steps. So in the homework assignments for this material, I will literally have you analyze these problems in these exact same steps. If you do it on your test like this, you're guaranteed to get it right, okay? So the first thing that we are going to do is we're going to analyze our circuit at t is equal to 0 minus, okay? So at t is equal to 0 minus, oh, and I guess we should define some quantities here. So let's call this VC of t. What other things might we want to know? Let's pick what we're going to solve for. So we're going to solve for VC of t for sure. What else do you want to solve for? Current through the inductor. All right. Let's just leave it at those 2 things. Now, those are our 2 quantities that we're specifically trying to find. We are likely going to need the inductor current. And technically, we're going to need the inductor voltage as well. Excuse me, not the inductor, the capacitor current. We're going to need the inductor voltage as well, but the inductor voltage is the same thing as the capacitor voltage, so I don't actually need to keep track of that. All right. So at t is equal to 0 minus, our circuit is going to look like this guy, right? We're going to have a 5-volt source. We have a 1 kilo ohm resistor, a 10 kilo ohm resistor, the short circuit represents our inductor. The open circuit represents our capacitor. So this will be VC at 0 minus. This will be IC at 0 minus. This will be IL at 0 minus. So it should be pretty obvious that IL, actually, let's do this differently. VC at 0 minus, its value. Justin, do you have any thoughts on what VC at 0 minus will be? I disagree. So for VC to be the voltage drop over the 1 kilo ohm resistor, the capacitor would need to be in parallel with the 1 kilo ohm resistor, and it is not. It's in parallel with the 10 kilo ohm resistor, which, as you mentioned, is shorted out. So what's the voltage drop over a short circuit? Zero. So VC is 0 volts. It's all right, man. We'll get it. Sarah, what's the current flowing through the capacitor at T is equal to 0 minus? Exactly right. 0 amps. Juan, how would I determine my inductor current at 0 minus? Current flowing through my short circuit. How do I get it? 5 volts over 1 kilo. Exactly right. That would be 5 milliamps. And that's our analysis at T is equal to 0 minus. Anybody got any problem with that? All right, pretty straightforward, right? Step 2. We'll analyze the circuit. T is equal to 0 plus. So at T is equal to 0 plus, our switch is opening up, which is effectively disconnecting this 1 kilo ohm resistor and this 5 volt source from influencing what's happening to the 10K, 4 Henry, and 12 microfarad components. So I'm not even going to bother drawing that voltage source in the 1 kilo ohm resistor anymore because it doesn't do anything. Okay. So we're going to have our 10 kilo ohm resistor here. And then we have our inductor, which I'm going to represent by a current source having a value of 5 milliamps direction down, because the current flowing through an inductor cannot change abruptly. So whatever value it had at T is equal to 0 minus, it has to continue to have at T is equal to 0 plus. Our capacitor is going to look like a 0 volt source, which is nothing more than a short circuit. So let's call this guy IC at 0 plus. So we know that VC at 0 plus has to be 0 volts. We also know that IL at 0 plus has to be 5 milliamps. And as a reminder, we know this because those are the two quantities that cannot change abruptly, right? So if the capacitor voltage was 0 volts at 0 minus, it has to continue being 0 volts at 0 plus. If the inductor current was 5 milliamps at 0 minus, it has to continue being that at 0 plus. So the only thing that we need to know that we don't have is our capacitor current. Sunny, what should my capacitor current be? So that's going to be part of it, but let's think about the directions here, right? So we have 5 milliamps flowing down in this middle branch, and that has the option of flowing through the 10 kilo ohm resistor or the short circuit. All of it's going to flow through the short, but it's going to be flowing up. IC is defined as down. So would you care to revise your answer? Negative 5 milliamps. There we go. All right. Step 3, which we're not actually going to do, would be to analyze the circuit at T is equal to infinity. The reason that we don't need to do it here is because there are no sources connected to our system at T is equal to infinity. So we know that all three of these quantities are just going to be 0. So really no need to go through the analysis there. All right, so our fourth step probably one of the most critical to getting our analysis correct, is to calculate alpha and omega naught and determine whether the system is critically damped, over damped, or under damped, because that's going to tell us how to do the rest of the problem, right? So in this case, alpha is 1 over twice RC. So that's 1 over, sorry, my thing moved on me here. 2 times, let's see, R in this case is going to be what? Why don't we include the 1 kilo ohm resistor? Exactly right. So the 1 kilo ohm resistor is disconnected during the transient condition, so it shouldn't show up in our equations. And then C was 12 microfarads, if I'm remembering correctly. Calculator. Yes.
So we're able to assume that the short circuits are ideal and have no resistance, but we can't also assume that that no energy is lost due to like heat or all energy conversions after you close the switch or after you open it. You're assuming some things to be ideal, and then you're assuming other things to not be ideal.
No, I'm assuming everything is an ideal. So the energy losses to heat are because of the resistor, which that's what a resistor does, is literally convert energy to heat. So we are dealing in a completely idealized circuit here. So if we had a practical circuit, right, our inductor would have some amount of resistance. The resistance of wire as compared to a 10 kilo ohm resistor is going to be so small as to not make any difference, right? Unless we had like a mile of, a mile of wire or something coiled up to make our inductor, it's not really going to affect anything. Similarly, technically speaking, the capacitor is also going to have some small amount of resistance, and any circuit element that is part of a closed current carrying loop exhibits a small amount of inductance as well, but they're going to be so small as to not really influence things. Okay. All right, so if we put in our numbers here, I get an alpha value of 25 over 6 neppers per second. Anybody else get that? Great. Omega naught is L times C to the -1/2 power. So that is, what was it, 4 henries times 12 microfarads. Flip it over and take the square root. And I get 144.338 radians per second. So based on these results, Jake, is this circuit critically damped, overdamped, or underdamped? Underdamped, exactly right. Okay, so which quantity do you guys want to solve for first? The capacitor voltage or the inductor current? Inductor current. All right. So step 5, I'm just going to call it math. All right. So since our circuit is underdamped, we know that it will have a response of the form B1 cosine omega dt plus B2 sine omega dt e to the minus alpha t. And I'm purposefully not writing the plus IL at infinity because we know that bit is 0, right? So what does this equation simplify to at t is equal to 0? So what happens to the exponential bit out here? E to the 0 is just 1. Okay, so this bit looks like 1. Then we're going to have B1 times cosine of 0. So what's cosine of 0? 1. So we're going to have B1 plus what's sine of 0? So we're going to have B1 plus 0 times 1. So IL at 0 plus is just our coefficient B1. And from our analysis, that is nothing more than 5 milliamps. So we already know halfway how this inductor current is going to behave. Ian.
Was it negative at the 0 plus?
IL was 5 milliamps.
Right. Current was.
Right. Capacitor current, yes. All right. Our inductor voltage, which is the same as our capacitor voltage, will have the following form. This is pulled from the table. I've derived it once, and that's the only time I want to do it. So we're using the table from here on out for these derivatives because it's a pain in the butt. Sorry. So this is going to be L VI by dt. So that's why I give you guys the derivatives. We need to remember to multiply by the L on the outside, or we're going to get the wrong answer. So we're going to have L multiplied by omega d B2 minus alpha B1 cosine omega dt minus omega dB1 plus alpha B2 sine omega dt e to the minus alpha t. And sorry, that went away. So our inductor voltage at t is equal to 0 plus. What is this going to reduce to when we substitute t is equal to 0 in? So this part goes to 0. This part goes to 1. This part goes to 1. So V of L at 0 plus is just going to be L multiplied by this guy right here. Well, we already know, oh, excuse me, and that's going to have a value of what? So what was the actual solved for capacitor voltage at t is equal to 0 plus? 0, right? So if we take a moment to calculate what omega d is, we have enough information to solve for our unknown coefficient B2. Right? So let's do that real quick. Up here, omega d is the square root of omega naught squared minus alpha squared Sinusoids, yep. So I get omega D to be 144.277 radians per second. And so I can say that let's see, so let's do a little bit of math here, okay? So alpha times B1 will be equal to omega D times B2. So B2 for this guy right here will just be alpha B1 divided by omega D. My algebra is correct. It's not by all means tell me, but all I've done, I can divide both sides by L, which effectively just gets rid of the L since I'm dividing 0 by it. And then I moved the alpha B1 to the right-hand side of the equal sign, and then divided both sides by omega D. And so that gives me 25/6 times 0.005 divided by, that answer I just got a Z. $144.398 microamps. And so I can plug those values in, and I will find that IL of T is equal to 5 times 10 to the 3 cosine 144.277 T plus 144.398 times 10 to the, oh, that should have been a minus 3, 10 to the minus 6 sine 144.277 e to the negative 25/6 t. All right, so we're a little low on time here. So if we wanted to calculate what the capacitor voltage was, what would we have done differently? Literally, we would just put VC here and IC here, and our analysis would be exactly the same, but we'll wind up getting different values because those are equal to different things. Okay. So what I want to use the next 15 minutes for, if it takes that long, which it very well may, is to show you how to use LT Spice. Yes, Brandon. All right, so LT Spice. So there we go, behind stuff. All right. Now, there is a way to implement switches and all that kind of crap in LT Spice, but I don't feel like doing it because it takes a lot longer and this is pretty straightforward, okay? So I am literally just going to put a resistor and inductor and a capacitor in parallel. Wire things up. And I have to give it a ground or LT Spice won't do it. So I'm just going to choose the negative polarity terminal of my capacitor voltage to be ground. Okay. This was a 10 kilo ohm resistor. This was a 4 Henry inductor. This was a 12 microfarad capacitor. And what I'm going to do now is I'm going to go and click on this .op thing up here at the top right. And I'm going to set my initial condition.
I'm not sure I understand.
Shut up, watch. All right, so my initial conditions will be as follows. So I'm going to do .ic. So initial condition, I, open parentheses, L1. So that's saying the initial condition on the current flowing through my inductor was 5 milliamps, right? I press Control M to get a new line. .ic, the voltage at node 1, which is the same thing as my capacitor voltage in this case, because there's only one node that isn't ground, was 0 volts. Okay. So I'm just putting in the values that I got at t is equal to 0 minus for my, to get the initial condition on my capacitor and the initial condition on my inductor. I'm going to press OK and drop these guys down here. I'm going to do a transient simulation. And let's see, so my alpha was 25/6, right? So that's telling me how long this thing takes to decay. So in this case, it's behaving a lot like a time constant, where 6/25 would be the time constant, right? So let's see. If I make this 10 times as long, 60/25. So let's call it 2.5 seconds. We're giving it plenty of time to see what's going on there. And just drop this guy down here and run my simulation. We are interested in the inductor current. So this is what our inductor current looks like. The squiggles and all that kind of stuff indicate that this is indeed an underdamped system. And it looks like everything is settling down before 1.5 seconds. So I'm going to change this to now be 1.5, just so I can get a little better picture of what's going on. So I just got a good estimate to see what was happening. So before we move on to the next bit of this here, I want to point something out to you guys. When you turn in your simulations for these problems for your homework, the expectation that I have of you is that I can see what's happening. And what I mean by that is I want to see how it behaves at the beginning, and I want it to end when it settles. So if I had something like this, where I did transient of 0.1, that isn't good enough because I can't see what it settles to, okay? Similarly, if I did it for 100 seconds, that isn't good enough because I can't see what's actually going on, okay? So you're going to need to play around with the length of your simulations to show me an accurate representation of what the circuit's doing without including a bunch of dumb stuff that doesn't really tell me anything. All right, so let's go back to 1.5 seconds. And rerun my simulation. All right, so this is the important part here, how we check our work. I can right click on my graph and I can add a trace. And I can literally type in a mathematical expression here where it says expressions to add, okay? So if 5, 0.00, so that's 5 milliamps times cosine. So omega D is expressed in radians per second. LT Spice wants it in hertz. Okay, so we're going to have to do a conversion factor of 180 over pi. So this is going to be, sorry, let me scroll up here so I can see what that number is. 144.277 times 180 over pi, or I can literally just pi for pi, multiplied by time. Plus, what was the coefficient for my other bit?
44.398 times
144.398 e to the minus 6 times sine 144.277 times 180 over pi times time multiplied by exp of negative, let's see, so that would have been negative 25 over 6. .1666666 blah 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 times time unknown.
Before the big bracket for that.
Thank you, Ian. Oh, why is it doing this to me? Let me double check things here. Oh, I didn't put one there. There we go. All right, so we can see that things look pretty good, but they're not quite right. All right, everything seems to be matching up pretty well, but the amplitude of my simulation is slightly smaller than the amplitude of my mathematical function. Anybody tell me what the problem is here?
You don't have
The scale on the left-hand side and the scale on the right-hand side are not the same thing. So we need to fix that. So make it from 5.4 to negative 4.5. And this shouldn't particularly matter, but I'm going to change the tick and I'll be damned. I match up perfectly. So this is how we can use LT Spice to check the results of our analytical analysis versus a circuit simulation to prove whether or not we got a problem correct or incorrect. Okay. For these underdamped circuits, if we don't put in this 180 over pi conversion factor here, our answer is going to be wildly wrong. Okay, so let me just prove it to you real quick. Vastly different. Okay, so it is absolutely imperative that you take into account LT Spice works in linear frequency And our analysis is in angular frequency, and you need to do a conversion there, okay? So you must convert omega D to degrees per second by multiplying by a conversion factor of 180 over pi, or you can be doing everything correctly and your simulation will tell you you're doing it wrong, okay? As I pointed out a couple of minutes ago, it is imperative that you make sure the scale on the right-hand side for your mathematical expression is the same as the scale on the left-hand side for your simulation, so that you're actually comparing apples to apples. And that's another place where you can be doing everything perfectly right, but the scales make it seem like you've made a mistake, okay? For this particular problem, so we could fix that by just putting units of amps here, and it would work itself out. That being said, for critically damped circuits, when we have to multiply a coefficient times time at the beginning, for whatever reason, like if you put amps per second or something as a coefficient, it doesn't like that. So you, LT Spice kind of freaks out. So I've just gotten in the habit of not including units in my checking my result and just making sure that these scales match up. All right. Anybody got any questions about anything else?